Hello everyone, in this lesson we're about to learn how can we process multi-zone parameters. That means instead of a constant for a parameter like salinity, like porosity exponent m or something like that, we will have different constant or different parameters per formation or per zone. So let's start with almost a synthetic example. So we have here to the right already processed example with formation from Dinwoodie, formation Phosphoria, formation Thames-Lip, formation Amsterdam, and Madison. And nested inside the Amsterdam formation, we have members, like the Horseshoe member and Darwin member inside Amsterdam. So each zone will have different parameters. Ideally, you have contiguous zone. That means the base of the formation should be the same as the top at the next formation and so forth. So here we made in purpose that the base of Dinwoodie doesn't touch Phosphoria top. So we have here a gap, we have a void, like a hole. We did that in purpose so we can show you how can we deal with those cases, and even we can assign a default behavior when the stratigraphy has some holes and some blank, some void spaces, and how can we process that and deal with a default value. Here in Amsterdam, we will have a property inside Amsterdam, but when the depths are touching Horseshoe and when your depths are touching Darwin, we have different parameters inside. And here we will have the Amsterdam parameter. Let's go now to the left. These are the original curves. We will be working only with those curves. So here you go to display, stratigraphy, you have your stratigraphy. Here you have formation, Dinwoodie, Phosphoria, Thames-Lip, Amsterdam, and Madison. And inside Madison nested, we have Horseshoe and Darwin. So the first thing we have to do is to define an indicator curve that tells the software where you are in Dinwoodie, when you are in Phosphoria, in Thames-Lip, Amsterdam, Madison, Horseshoe, and Darwin. So we have to build an indicator curve that indicates which depth is related to each zone. So there are several ways you can do that in YOLOIL. Probably the easiest way is to use the upscaling and filter tab here, right here. And let's do those fillings. Complete the data there. So for the template, you go to upscaling and filtering and fill this. So let's start with the first formation, Dinwoodie. We are about to type Dinwoodie flat. Dinwoodie flat. Type the description. Let's copy and paste the description from here. Control C, Control V, and choose the same color. Select the same color. I think this is the one. Now, here we are. Hit on open. Let's try to do the same. Let's click on active. You hit all of them active when you run all the upscaling in sequence. Open that. Copy target. Cross and cutoff. We are not going to filter anything. You unclick those. And zonation. So you are going to process the hot column. You want to produce a curve, so you fill here optional new curve outputs. So we want to detect a sum, or lithotype or something like that. And we need to filter by formations. Formations here. And the formation name is Dinwoodie. So this is a regular expression. You have to close that inside slashes in Woody. Now we have to detect some indicator flag curve. Let's assign a mnemonic, the name of the curve, and a short description. Let's copy from here the Woody flag and flag measure depth for the Woody. Everything is ready to process that. That's it. So let's hit compute and see what happens. The original curves. Let's compute and it will produce this curve. Let's see what happens. Compute. It's done. Let's see on curves. We have this one. We have this one. Let's see that curve as a edit table in the edit table tab. So let's see. You see in very shallow depths, Yoroi uses more than a binary logic, Boolean logic. Yoroi uses a complex trillion logic. That means we are processing 3 states. In Yoroi, a curve can have, in amount of information can have 3 states. That's for indicator variables. When we have 0, that means to Yoroi, well, I do not know what happens here, 45 feet. You see that the data start here, 344, exactly there. From 344 and shallower, we don't have any information. That means to Yoroi that we do not know if that is Dinwoody. Maybe it's wrongly assigned or missed or whatever. Okay, then Dinwoody, you see, start here from 344.5. Start here. And it spans up to 450 almost. So it goes to here and to there, 450. Okay. So here we have 1. That means that Yoroi knows that that is Dinwoody. That is Dinwoody. After that, we have 0. This blank zone, we do not know what's there. It really is Dinwoody, but we made in purpose, we shortened Dinwoody to show this behavior. Now we have Phosphoria. Check this out. We have Phosphoria 468. 468. Okay. Why -1? -1 is the state to say, I know that that is not Dinwoody. 0 means I do not know. Right here. Blank. 1 means I know it is Dinwoody. 0 means I do not know. There is a blank. And here we have -1. This is -1 because this is Phosphoria. And Yoroi perfectly knows that this is not Dinwoody. After Phosphoria, there is a blank here, around depth of 700. Let's go to there, something like that. 700. Go to depth. And that's it. That's 0. 0 means I do not know. From here to there. That means I do not know. Good. It's time slip that it starts in 742. That one. That means a no. Means a -1. Time slip, then go Amsterdam. All of this will be -1 because we know that that is not Dinwoody. That is the Dinwoody flag. Let's plot Dinwoody flag right here. So here we have 0, something like that. plus 1. In Dinwoody, we know this is Dinwoody. There is 0. You see this gap. There is 0. We do not know what is that. Then con minus 1 because we're in Phosphoria, and if we're in Phosphoria, we know, we have the knowledge that we are not in Dinwoody. Then it goes at 0. This one, this blank, this gap is a 0. We do not know. The stratigraphy is incomplete there. And after that, we have minus 1. Because Ten Slip is not Dinwoody. Amsterdam and so forth is not Dinwoody. And here we have a gap, so it should be 0. And you click here and you read exactly 0. You see 0, minus 1, and so forth. And plus 1, it is only in Dinwoody. Okay, let's replicate that curve here. You go to display, step tracks, put the curve numbers. Okay, the curve number is the number 8. The number 8 in some flags, the number 8. Okay, you can skip to step 3. The woody flag, let's choose a color. Let's choose something like gray, something like that. And okay, so the minimum and maximum of the curve minus 1 to plus 1, but we wouldn't like to those values touch exactly the walls of the frame. So let's go a little bit to the left, a little more to the right, minus 1.5, 1.5. The stroke, we have several types. Solid is recommended for solid curves itself. Here is better go straight lines, pure lines, constant lines. And thick. Let's put a thick pattern. Good. Let's make the display. That's the same. Choose a darker color. Something like that. Darker. That one, for instance. Okay, let's highlight exactly the belonging to Dinwoody. Dinwoody is 1.0, this zone. Let's make a feeling of that. So the Dinwoody flag, you choose threshold. To the left, let's put white and transparent. And to the right, let's choose gray. Something like the former gray. Let's choose some transparency, maybe, I don't know, maybe 50% on that. And the threshold value to the left of minus 1 will be white. And let's put the filling from 0 and beyond and see what happens. Exactly. So this is Dinwoody. This is the only zone, the only collection of measured depth where you have Dinwoody. There is another thing, you see, we want to process only the petrophysics from this start depth and this end depth. There are many reasons for that. You want to concentrate in pay zones. Another reason is your logs are reliable from this depth to other depths. So you go to step 1 track and depth, and you can specify this. So instead of processing the whole column, you want to restrict your computation, your petrophysics. The indicator curve is the number 1, where you can put any one. But 1 is like measure depth is the default. The column number 1 is always measure depth. So we want start from 400. You type here 400. And the final depth, the maximum signal will be 1390. That one. Okay, that's all. Let's undisplay the curves and put a non-TBD scale. You do the same for the other formations. Like Phosphoria, let's do quickly Phosphoria. Go to obfuscating and filtering, obfuscating. You add, this is the reference, add Phosphoria, Phosphoria flag. Let's add that. Phosphoria flag. Okay, active. I think the color is this one. Was already saved. Anyone you put a new color is saved here in recent or recent. Copy here to there. No color filtering, zonation, the whole column, detect the zone, and filter. By formation. And we're processing now Phosphoria. This is a regular expression, has to be enclosed into flashes, Phosphoria. And put the mnemonic for the curve and a short description. It is a flag. Let's copy and paste quickly. That one. What else? Run that, compute that, and see what happens. Let's compare Dinwoody and Phosphoria flag at the same time. Let's see how it behaves. Okay, so it starts with 0. That means here I'm shallower than that. We don't have nothing. We do not have any knowledge of the stratigraphy there. So it starts with 0. I do not know, says Joloi. Then you go deeper and see this. This is the Dinwoody flag. Here starts Dinwoody. And what about Phosphoria? Phosphoria here starts with -1. That means, since Joloi knows that this is Dinwoody, Phosphoria is a no. Phosphoria means I know that this is not Phosphoria because it's Dinwoody. You go deeper, what will happen in this region? This blank. You go deeper. Here is a 0 zone for both Dinwoody and Phosphoria. There is a blank. We do not know nothing on that stratigraphy, so there is a 0. Then you go to the next. We have 468. This is Phosphoria. So what happened with Dinwoody? It means, well, I know it is not Dinwoody, so it is -1. I have the knowledge that it is not. And Phosphoria is +1. That means I know this is Phosphoria. 3 values of logic. So +1 means I know, and the answer is yes. -1 means I have the knowledge, this is a no. And 0 means I do not know anything. So we're handling uncertainty. You have 3 states of logic. It's more than Boolean. It's quite complex. And very useful. Okay, you go deeper. You reach more or less these depths. And there should be, what it does should be zeros. Let's go down. Okay, 0 for both the Dinwoody flat and Phosphoria. So it's zeros. Means I do not know if there is a Dinwoody or Phosphoria. I do not know anything. Maybe a different thing, but so far I do not know what is there in the stratigraphy. You go deeper, and then you hit hitting 10 sleep around 740, and that's it. 742. It starts 10 sleep. You see the stratigraphy. It's 10 sleep. Okay, start here. Close to 742. 742. Then it's 10 sleep. That is 10 sleep, but we are processing Phosphoria, so Joloi knows, it has the knowledge that this is not Phosphoria nor Dinwoody. after 10 sleep you hit Amsterdam will be -1. All of them will be -1 because we have the knowledge that those are not Phosphoria. All the way down will be -1. At the end we have some zeros because we have this blank of knowledge. And so forth, we continue developing, defining the next songs. In the same token, we define the next indicator flags for 10 Sleep, Amsterdam, Madison, Horseshoe, and Darwin. Okay, let's see what are the curves produced. These ones. So we have Dinwoody, Phosphoria, 10 Sleep, Amsterdam, and Madison. Dinwoody, Phosphoria, 10 Sleep, Amsterdam, and Madison. Let's see in the view of edit table how they look. All of them start with 0. 0, we do not know the stratigraphy right there. Then we start touching Dinwoody, and the remaining indicators are in -1. That means we have the knowledge that they are not them, but Dinwoody. So we are not, this is for 40, we know that this is not 10 Sleep. We do know that this is not Amsterdam, and we know that this is not Madison, but it is Dinwoody. If we keep going forward deeper, beneath this, we have an unknown zone, this one a blank here, everything is 0, that means uncertainty. Then we hit Phosphoria here. So we know it is Phosphoria, and we have the knowledge it is not Dinwoody, nor 10 Sleep, nor Amsterdam, nor Madison. You keep going, then you will hit a blank region here, which everything will be 0. You move there. 0. And then you start hitting 10 Sleep right here. Start hitting 10 Sleep. And after 10 Sleep, you need to hit and call the Amsterdam and Madison. Amsterdam and Madison. Now we have nested members inside Amsterdam, Horseshoe, and Darwin. Let's define those and let's explain to you how can we do that. Okay, you append new and choose the color for Horseshoe, maybe this blue or green. Let's call this Horseshoe flag. And we can copy the description from the right window. Open, open, no filters by curves, zonation, detect the zone, and filter. Filter by members. Those are members, no longer formation. Hit members, and you have to seek for the word Horseshoe. When you Horseshoe, it will go to stratigraphy internally and will match this title. And the mnemonic for the curve and the description for the curve. Now it's members instead of formation. Let's run that and see what happens. Okay, you created a curve with this horseshoe flag. Let's go and see all of them at the same time. Edit table. So we are in Amsterdam. Let's see. In Amsterdam we have horseshoe. Let's go to the top of that. This is Amsterdam, perfect. This is the region of Amsterdam. -1, here's -1, then +1. And what about Madison? Let's see what happened with Madison. We know those there are for Amsterdam, but not from Madison because it's -1. If you go deeper, let's see what happens. This is Amsterdam. It is not Madison. And now here, what happened? Perfect. Now here, okay, look around these depths. This depth is around this depth. So we know this is Amsterdam. We know this is not Madison because it's -1. And what about horseshoe? Horseshoe here is blank, so we do not know everything. Now, this is horseshoe. Is at the same time, it is horseshoe, and at the same time, it is Amsterdam. That is because horseshoe is a member nested inside Amsterdam. You go there, then disappears. There is a blank here. Then disappears, and then starts Darwin. So, okay, now -1. So Deloitte handles nested songs without any problem. Let's do the same for Darwin, the Darwin member of Amsterdam inside nested. Okay, we have defined now Darwin as a member inside formations and see how it look the curves. So you highlight all of them, edit table, and let's go around this depth. Let's go 1182. This is a region of I do not know. This is blank, 4 members. So it knows it is Amsterdam, but we do not know what is the member. That is 0. Then you go here. You start horseshoe. And Darwin flag is -1. So this is horseshoe. And we know this is not Darwin. And this is not, this is Amsterdam, but it is not Madison. You go deeper, you enter this region. This is a 0. So it is Amsterdam, but it is, we do not know what is horseshoe or Darwin flag is 0. And then finally we have Darwin. We hit Darwin here. It is at the same time Darwin, it is at the same time Amsterdam. It is nested Darwin member inside Amsterdam formation. So these are the indicator flags. Now there is some an additional zones marked here. So we have formation, and nested inside formation, we have members inside formation. Now, let's define a multisome property like salinity. In this example, we know from research data, from lab data, that we can have perfectly different salinities per formation. That is quite typical. Different environment, different geology, different water migration, dissolved minerals, whatever. So it's quite typical. This is the correct way we should model. So now we have to define a function to define salinity. There are several ways to do that in YOLOIL. So we're explaining now probably the best way, the most compact way, easy to understand. But there are many ways you can handle YOLOIL in many different ways. So you hit workflow, and let's start with those equations, salinity. Okay, you start with salinity, and the description, copy from here, variable salinity. This is quite important for a good model. So when you think about a constant, think twice before consider it is a constant. Constant means that either it is a real or movable value, or there is a constant per different formation. The most usual case is it is a partial constant. There is a constant for one zone, there is a partial constant for another zone, and so forth. That is like a stepwise function. Color, like pure red, salinity model. Deselect, salinity, open. So let's fill this information. The output data tab. The mnemonic, let's call that salinity. Units parts per million of equivalent sodium chloride. The description. Now, there are several ways to do that. The easiest way, well, maybe it's not easiest. One very effective way to model that is to use YOLOIL login scripting language. So we're about to write a short script, very powerful and very general. If you want to learn about YOLOIL scripting, you may hit here, scripting tutorial. You have some examples, explanation of how to do that on the website, on our website. And you want the reference of the question, you hit scripting manual, and it will open the collection, the reference manual of the available function, explanation how to use that, and more explanation. These are comments. It starts with design, hashtag, number tag. Let's copy this here. Okay, this is some help with that. Well, measure depth is always the core number one. Now the flags. The flag curves are this one. Dinwoody is the curve number 8. Phosphor is the number 9, and so forth. Okay, Dinwoody 8, Phosphoria 9, Tensley 10, Amsden 11, and so forth. So you have to declare that into YOLOIL. Go to functions. It is exactly the same, so we can copy that from here to there. Now let's define a value that is the salinity of Dinwoody. Let's suppose from some lab data, we know that the salinity is now We're using the blank function. So we want to say that Dinwoody salinity is 3500. Yes, that is true. But we have to declare that only for the flag of Dinwoody. So what we need is to use the function. You remember the flag means 1.0. It means that is Dinwoody. 0 means I do not know. And -1 means I know it is not Dinwoody. So what we want to do is to use the blank function, this function. So this function is 1 if the first argument is larger or equal than the second one. So we are using the Dinwoody flag, blank, Dinwoody flag, and has to be larger. We want to capture 1. So it has to be larger than 0, not larger or equal. So to avoid, to remove, do not include the 0, we can put 0.01. So that will yield 3500 if we are in depths that belongs to Dinwoody, and for depths that are not in Dinwoody, or we do not know, will be assigned minus 999.25. We do the same for the next ones. Now Phosphoria, the salinity is Phosphoria is 3260. The salinity of tank sleep is 2800. Amgen 3500. 4000 for Madison, 3700 for Horseshoe, and 3780 for Darwin. They are different. They do not collide because we're using the blank function. Now, what happens here? What happens where we do not know what is that? In these gaps, there are several things we can do that. One thing is to give the result is -9, so we do not assign any salinity. And another approach will be to assign a default value or a background value for there. Let's meanwhile ignore that, ignore this, and put the default value. Okay, now we have to merge all of these values. So we can define a salinity, and ACL will be the merge. We'll merge those internal curves. Okay, remember to use the manual for merge. This is the explanation. An explanation how to do merge curves. Read this. The first priority curve is Darwin. That means that if we're in these depths, around these depths, what is the value you want to assign? We have both value for Amsden, 3500, and also have value for Horseshoe, 3700. But we know we're in Horseshoe, so Horseshoe has to take higher priority than Amsden. So merge, the first priority is Darwin or Horseshoe. Darwin or Horseshoe. They don't collide. And then the remaining zones. Clear, okay, clear. You hit calculate, well, not active. Well, you hit active and that's it. Clear, calculate. Let's see the result in tabular view. edit table, start from the beginning. So salinity, you remember the zero. The zero status means I do not know. So now we have to assign a salinity. That has to be a numerical value, not a logical value or trilogic value. In this case, an unknown value is minus 999.25. That is the unknowledge. Because salinity is a number, will be a number that enters into equation. Minus 999.25 is the gold standard in petrophysics that says, well, I don't have information on this value. That is a missed value that will be minus 999.25. So this is an important difference between logic curves, trillion logic curves, and numerical real value curves. Let's see. So it starts, here is not known the salinity. Then we start hitting Dinwoody. Okay, we start hitting Dinwoody, but what we have minus 999? That is correct, because you remember we defined the geoloid to start the process on these depths, something like this. So you will start from these depths to that. Okay, from here to there, we will have the salinity Dinwoody, 3500. 3500. Then you go deeper, deselect. Perfect. It is not known. That is this region here. Now the next is Phosphoria. You remember in the script, Phosphoria is 3260. You go deeper, you hit that. Perfect. You see the indicator for Phosphoria is 1, and the value is 3260. In a single curve, we have a variable curve. So it's not a constant, but a stepwise constant, to say in some way. The next value here, okay, step for 4 will have a missed value, minus 9 here, as indicator will be zeros, but for numerical value will be minus 999. You see minus 99. Then go to the next. You hit 10 sleep, go deeper in the bar, and for 10 sleep, the value should be 2800. Let's go to horseshoe is around 1212. So you go type here 12, 12, 12 is here. Perfect. So you see here, okay. Okay, let's see. So it takes here Amsterdam, and that should start. It isn't also in Amsterdam, but it should take the horseshoe value, and when horseshoe ends, it will take again Amsterdam. Amsterdam, 3500. Then start taking horseshoe with 3700. If you go deeper, it will. If you go deeper, it will capture again Amsterdam. Perfect. And then Darwin. This is Darwin. And then Madison, this 4000. Now, we don't like those gaps. So we need to process water saturation or many other properties. We must have a salinity here. There are ways to do that. One way is to completely define the stratigraphy. and it will fill, then you won't have any gaps or any minus 999.25 salinity. An interesting choice will be to define a default value, like this one. For when this minus 999, there is no knowledge replaced with the default value. So default value, you will try to merge all the curves, and if nothing is found, the last curve will be this one. So let's do that and see the difference. Okay, before that, let's make a plot so I can show you how it behaves the salinity. Make it clearer. So go to the salinity track and add salinity. Add salinity. Let's take a guide here. Okay, let's put that in red. That one in red. Okay. Salinity, it ranges from 2800 to 4000. So let's go a little bit to the left, a little bit more to the right to avoid to touch the walls of the frame. Maybe 2700. And here 4100. Stroke straight. Let's put thick and red color. Let's see how it behaves. This is it. So these are the gaps you see here. Salinity minus 9. This is the gap here and the gap here. This is the value, and this gap is this gap minus 9. It's behaving perfectly as was designed. And here we have the base of Amsterdam, 3500. Depends how you collocate. Put the mouse, use kill. Okay, but if you hit horseshoe, jumps to horseshoe value. Because horseshoe takes priority over Amsterdam because it's nested inside Amsterdam and we do know the value. Then the default, the former local default as Amsterdam, and then the value for Darwin, and then the value for Madison. We want to fill these gaps we don't like. That is why you can guess or assign a default value for salinity because you would like to produce some water saturation values. So let's do that. Let's do that. Define a default value, something like that. Let's suppose the default is around 3000. That's it, and put a comment if you want. So all on defined zones, all the salinity that formerly were minus 99.25 will take now this value. And you say, well, in the last probability on the merge, take the default, this one, take this one. Now, rerun that, calculate that, and see how it modifies the curves. Okay, perfect. Now the default value, we have a default value of 3000, formerly was minus 9 here, and here we had formerly minus 999.25. Now we have the default 3000. Perfect. Make in the display a filling on that. Filling.curve, salinity compared with a threshold. Okay, I want to the left to be transparent white. You hit white and 100 on clear transparency. And this is red with around 50% transparency. Now you choose to the right of the threshold, put red. This is red, 50%. And now put a threshold value. So to the left of 0 and to the right of 0. And see how it behaves. And that's it. Very clear. So you have 10 slip, low salinity. We have Amsterdam, higher salinity, and so forth. The salinity curve is a stepwise constant. It's not a full constant, but a stepwise parameter constant. Each different zone will have different constant, local constant, to say in some way. Now, why this is important is you need to compute water saturation, you need the formation water resistivity, and the formation water resistivity depends upon salinity. Let's do that. Function workflow. Okay. For that, we need to define temperature and formation water salinity. The next workflow, define something default temperature. So you do not know too much information on your well, your temperature profile, you can define a default. Let's see how to do that. Open, write the mnemonics unit, temperature, mnemonic, unit Fahrenheit, borehole temperature, and we choose the equation 11, resistivity equation 11, you go there, equation 11, let's see. Well, in this particular example, you choose you have to know what is more or less what the annual temperature of your reservoir at the surface for the surface temperature there. This is Wyoming. This is quite cold. The default geothermal grading is this one, and since we are assuming this is a vertical well, TBD is 1. This is assuming there is a vertical well. If the well is not vertical, you have to enter the deviation survey file, the trajectory file, and then compute a TBD curve and enter the number of that TBD curve. We usually put the TBD curve on the curve number 2. Okay, so far let's put in 1. You run that, it creates a curve temperature. Let's have a look on that curve together with salinity. See, the temperature starts cold and it grows slightly. You see change here in salinity, approach changes, temperature changes smoothly. Okay, you see clearly, temperature changes smoothly. As we deepen into the well, the temperature increases. That is important, especially you have a very thick column, so temperature starts 45. Here at ends around 60. In this particular example, this is a very shallow well. Now, function workflow. List now RW. Let's go with RW and choose a reference color, visual color, red, and call RW. Description, copy from here. Formation, water resistivity, a simple example. That's it. Open, and let's copy the mnemonic, the units, and the description for the former example. From the reference example, copy mnemonics, units, and description. Choose now the equation 8 in resistivity and temperature. Equation 8, that is a quite default regular expression. If you have the salinity through ionic water analysis or lab results or whatever, if you have the salinity and the temperature, you can have the formation water resistivity through an equation. It's internal in your oil. And also on the website. You can dig into the website, our website, you will find that. Okay, water salinity and RW. Okay, we have some of the theory. You can check this and see how we can assign formation water resistivity from salinity. So internally, Yellowit will use these equations. That's it. So some of the theory there. So we need the temperature. We already computed the temperature. You may go to curves and with 15 and 16. But if you have a lot of information, we have 100, 200 curves, maybe it's easier you hover the mouse here. Salinity 15 with an asterisk, that means that curve has been plotted. 15 and 16 temperature. Salinity is a curve, it's not a constant value. It's a stepwise parameter value. So we have to enter the temperature. Temperature is 16. And salinity is 15. It's not a constant, but it's a curve number 15. Okay, you hover on that, you will see temperature 16, and here salinity 15. That's it. Now, calculate that. And see that. Let's see those three at the same time. Edit table. Let's start from the beginning. Okay. Control click. Okay, we have a constant salinity where the temperature is slightly rising. And look what happened to RW. It's changing. In spite that we have the same salinity, it is changing because the temperature is changing. So we start with cold temperature and gets hotter and hotter. So RW goes to 2.4 and then drops to 2.3 or something. That is important. So it's feasible, do not use a constant RW. Let me repeat, do not use a constant RW, but almost in all the cases that is not true. RW is variable. It is a curve itself because the temperature is not constant. RW will decrease as temperature gets hotter. RW will decrease as temperatures goes hotter and hotter. However, if you have a thin reservoir, the range of RW will be more or less the same. It's like 2.38 is quite similar to 0.41, but it is not. So there is no reason why to handle a constant RW. You can use a variable if you have the correct salinity and a good temperature model. There is an stepwise. There is a jump on salinity. We have a jump on RW. We have a fresher salinity from 3500 to 300. So we have a jump on resistivity. We have fresher salinity. We have a higher formation resistivity, 2.75, and so forth. Let's make a display on this. In the salinity track, for instance, that's RW. Let's see this. Okay, let's pick a color like this blue, slightly smaller than the minimum and slightly larger than the maximum, maybe 1.6, and to the right something like 3.2. 3.0. Let's put 3.2 to have the same example. Let's choose a stroke parent dash and something like thinnest and see how it behaves. You see that? See how RW it is not a constant. RW decreases as the well goes hotter, the borehole was, the formation goes hotter, gets hotter with depth, and that's the behavior. This is all for now. This is our recommended way to handle multi-zone parameters which are not constant. Perhaps it's not very easy, but it's not very difficult. Once you complete yourself an example, you will master the technique. For very powerful, you can do merge and define defaults and overwrite members over formation and many things. This is a full feature logging scripted programming language. Thank you very much.